The ocean floor is a quiet place, but the journey to reach it is violent. On a calm spring morning in 1963, 129 men are erased from existence in a fraction of a second. It is the moment where the boundless optimism of the atomic age collides with the crushing reality of physics. To understand the tragedy of the USS Thresher, we must first understand the silence that followed it. It is a silence that still hangs over the United States Navy today. Every time a modern submarine leaves its pier in Groton or Norfolk or Pearl Harbor, it carries the ghost of this single morning. The safety briefings, the checklists, the obsessive attention to detail, these are not just bureaucratic requirements. They are the scar tissue formed over a wound that never truly healed. The date is April 10, 1963. The location is the North Atlantic Ocean, roughly 220 miles east of Cape Cod. The water here is deep, plunging down into the abyss off the edge of the continental shelf. The surface is relatively calm, with a gentle swell rolling under a gray sky. Bobbing on this swell is a small ship, the USS Skylark. She is a submarine rescue vessel, a humble support ship designed to stand watch, while the true leviathans of the fleet do their work below. The men on the deck of the Skylark are drinking coffee, checking their watches, and listening to the static of the underwater telephone. Far beneath them, the USS Thresher is conducting sea trials. She is the lead ship of her class, the most advanced, most powerful, and deepest diving submarine ever built by the United States. She has just come out of a long overhaul period, a tune-up to ensure she is ready for the front lines of the Cold War. Today is the final exam. She is conducting a deep dive test, pushing her hull down to its maximum certified operating depth. The mood is professional and focused. There is no sense of impending doom. On board the Thresher, the atmosphere is crowded. In addition to her standard complement of naval officers and enlisted men, the boat is carrying 17 civilian technicians from the shipyard and several naval observers. There are 129 souls on board. They are the best of the best, hand-picked engineers, veteran sailors, and brilliant designers. As the morning progresses, the Skylark maintains contact with the submarine via the UQC, an underwater acoustic voice system. The voice from the deep is distorted, sounding like a duck quacking in an echo chamber, but the messages are routine. They report their depth, they check their instruments. They are taking the boat down in steps, pausing to listen for leaks, pausing to check the hull integrity. At 9 a.m., everything appears normal. But by 9:10 a.m., the tone changes. The Skylark receives a transmission that is garbled, difficult to understand. The rescue ship asks for a repeat. At 9:13 a.m., a voice cuts through the static. It is calm. It is disciplined. It is the voice of an officer who is busy, but not yet terrified. "We are experiencing minor difficulty," the voice says. "Have positive up angle, attempting to blow." To a layman, minor difficulty sounds like a small problem, a tripped breaker, or a stuck valve. To a submariner, hearing those words at test depth is chilling. It implies that something is wrong with the boat's ability to sustain itself, but the crew believes they can handle it. The phrase, attempting to blow, refers to the emergency ballast system. They are blasting high-pressure air into the ballast tanks to force the water out and make the submarine light enough to rise. The men on the Skylark wait. They watch the ocean surface, expecting to see the massive black fin of the Thresher breach the waves in a spray of white foam. They wait for the emergency blow, which usually results in the submarine surfacing violently, like a cork released from the bottom of a pool. But the water remains undisturbed. 4 minutes pass. The silence on the underwater telephone stretches thin. The captain of the Skylark picks up the microphone and calls down, asking for a status report. "Are you in control?" he asks. There is no answer. Then, at 9:17 a.m., the Skylark's sonar operators hear a sound that they will never forget. It is not a voice. It is not the rhythmic cavitation of a propeller. It is a dull, heavy thud. It is a low-frequency crunch, like a heavy door slamming in a distant room. The acoustic energy of that sound travels through the water at 3,000 miles per hour. It passes through the hull of the rescue ship and registers on the strip charts of the sonar equipment. It is the sound of a catastrophic implosion. Down in the dark, beneath 8,000 feet of water, the pressure hull of the Thresher has failed. The ocean, pressing in with the weight of 2 tons per square inch, has instantly crushed the steel tube. The violence of this event is beyond human comprehension. The collapse happens faster than the human brain can process nerve impulses. The men on board do not drown. They do not suffocate. They simply cease to be. On the surface, the Skylark continues to call. "Thresher, this is Skylark. Over." They throw signal grenades into the water, small explosives that signal the submarine to surface immediately. But the ocean is indifferent. The debris from the Pride of the Navy is slowly drifting down to the silt, settling into a debris field that will become a graveyard. The Thresher is gone, and with her, the illusion of invincibility that defined the early nuclear age is shattered forever. To understand why the Thresher was there, and why her loss was such a profound shock to the national psyche, we have to look back at the era that built her. This story does not truly begin on the ocean floor in 1963. It begins in the shipyards of Groton, Connecticut, a decade earlier. The 1950s and early 60s were a time of supreme technological faith. The United States had unlocked the power of the atom. We were building rockets to go to the moon. We were curing diseases. There was a pervasive belief that American engineering could conquer any obstacle, whether it was the vacuum of space or the crushing pressure of the deep. In 1954, the Navy launched the USS Nautilus, the world's first nuclear-powered submarine. Before Nautilus, submarines were essentially surface ships that could dip underwater for brief periods. They ran on diesel engines and had to surface to recharge their batteries. They were tethered to the air. Nuclear power cut that tether. A nuclear reactor needs no air to operate. A piece of uranium the size of a golf ball could drive a submarine around the world 3 times without stopping. It changed the fundamental nature of naval warfare. Suddenly, the submarine was a true creature of the deep, capable of staying submerged for months. The Navy, led by the brilliant and demanding Admiral Hyman G. Rickover, embraced this new power with religious fervor. They built a fleet of nuclear attack submarines designed to hunt Soviet vessels and protect American carrier groups. The Thresher was the pinnacle of this evolution. She was the first of a new class, designed not just to be fast, but to be quiet and deep. The engineers gave her a hull made of HY80 steel. This was a new alloy, high-yield 80, capable of withstanding 80,000 pounds of pressure per square inch. It was tough, flexible, and incredibly strong. It allowed the Thresher to operate at depths that would have crushed World War II submarines like tin cans. Her test depth was officially classified, but it was known to be in excess of 1,000 feet. She was powered by the S5W reactor, a pressurized water reactor that was a marvel of reliability and density. It provided massive amounts of power in a compact space, driving the ship through the water with silent, deadly efficiency. The men who designed and built the Thresher believed in her. They believed in the math. They believed in the welding. They believed that they had mastered the physics of the ocean. We believed we had built a submarine that could not sink. A senior naval architect would later testify before a congressional inquiry. This was not arrogance in the traditional sense. It was the confidence of a generation that had won a world war and was busy inventing the future. The Thresher was more than a machine. She was a statement. She carried the most advanced sonar suite in the world. She carried the newest weapons. She was the Cadillac of the submarine force, the assignment every officer wanted. To be chosen for the Thresher crew meant you were the elite. When she left the Portsmouth Naval Shipyard for her sea trials that April, there was no fear. The sea trials were seen as a validation, a final check mark on a project that was already considered a triumph. The idea that the hull could fail, or that the reactor could stop, was considered a statistical impossibility. The systems had backups. The backups had backups. The engineering was robust. But faith is a dangerous thing in engineering if it is not paired with verification. The confidence in the Thresher's design masked a series of subtle, quiet dangers. The shift to nuclear power had happened fast, perhaps too fast. The technology of the reactor was light years ahead of the plumbing that supported it. While the nuclear heart of the ship was built to the most exacting standards imaginable, the rest of the boat, the saltwater pipes, the hydraulic lines, the ballast systems, was built using older, more traditional shipbuilding techniques. It was a spaceship wrapped in the skin of a steamer. The experts and historians who study this era, such as Norman Polmar, often point out this disconnect. We had placed a 21st century power plant inside a hull built with assumptions from the 1940s. We assumed that because the steel was stronger, the ship was safer. We assumed that because the reactor was perfect, the ship was invincible. As the Thresher pointed her nose down and began her descent into the cold dark of the Atlantic, she was carrying more than just her crew. She was carrying the collective hubris of a nation that thought it had solved the problem of survival at sea. The ocean, however, does not care about national optimism. It does not care about advanced degrees or high-yield steel. It cares only about pressure. The men on board felt the floor tilt as the submarine dove. They felt the air pressure in the boat change slightly. They watched the depth gauge spin, 400 feet, 600 feet, 800 feet. They were riding the marvel of their age, trusting in the genius of the men who drew the blueprints. They did not know that deep inside the complex maze of piping that ran through the engine room, a single joint, a connection between two pipes no bigger than a man's arm, was holding back the entire weight of the Atlantic Ocean. And they did not know that the faith placed in that joint was based on a flawed assumption. The tragedy of the Thresher is not just that she sank. It is that she sank because we believed she couldn't. The blind faith in the technology blinded the Navy to the microscopic flaws that were waiting, patiently, for the pressure to build. The descent into the abyss is a ritual. For the men on board the USS Thresher, the morning of April 10th begins not with fear, but with the steady, practiced rhythm of professional sailors doing a job they love. To understand the magnitude of the loss, we must look at the faces of the men who were lost. The Thresher was not just a military unit, it was a community. The commanding officer, Lieutenant Commander John Wesley Harvey, was the archetype of the nuclear navy. He was young, brilliant, and experienced. He had served on the Nautilus during its historic voyage under the North Pole. He had been handpicked by Admiral Rickover himself. Harvey was a man who knew his boat intimately. He trusted his crew, and they trusted him. Alongside him were 107 other officers and enlisted men. There were sonar technicians who could distinguish a whale from a Soviet sub at 20 miles. There were reactor operators who knew the physics of neutron flux better than most university professors. There were cooks who were already preparing the midday meal, roast beef and potatoes, in the galley. And there were the civilians. 17 men from the Portsmouth Naval Shipyard had joined the crews to observe the equipment they had spent months installing. These were men who lived in the local towns. who had families waiting for them back on shore. They were there to check the vibration of a turbine or the seal of a periscope. For them, this was a field trip, a chance to see their handiwork in action. At 7:47 a.m., the Thresher reports to the Skylark, proceeding to test depth. The dive begins. A submarine dive is a sensory experience. As the vents open and the ballast tanks fill with water, the boat becomes heavy. The bow angles down. The sensation of motion is smooth, almost like an elevator descending. Inside the hull, the world is brightly lit and climate-controlled. The fluorescent lights hum. The air smells of coffee, ozone, and amine, the chemical used to scrub carbon dioxide from the atmosphere. It is a sterile, mechanical environment that feels completely detached from the hostile world outside. But the hull tells a different story. As the Thresher descends past 400 feet, the pressure of the ocean begins to squeeze the steel. The hull literally shrinks. The diameter of the submarine decreases by inches. This compression causes the internal fittings to shift. Floor tiles buckle slightly. Locker doors pop open. The hull groans. A series of loud pops and creaks that echo through the ship as the metal adjusts to the immense weight of the water. To a rookie, these sounds are terrifying. To a veteran submariner, they are the music of the deep. They are reassuring. They mean the steel is doing its job. At 8:35 a.m., the Thresher passes 400 feet. The crew is at battle stations, not because they are fighting an enemy, but because the deep ocean is an enemy that never sleeps. Every man is at his post. Damage control parties are standing by with heavy wooden wedges and mauls, ready to plug any leak. At 8:53 a.m., the Thresher passes the 1,000-foot mark. They are now deeper than sunlight can reach. Outside the hull, it is eternal night. The water temperature is near freezing. The pressure is over 440 pounds per square inch. Captain Harvey orders the boat to level off. They check for leaks. They cycle the rudder. They test the propulsion. Everything is nominal. The reactor is purring. The boat is dry. The mood in the control room is calm. Conditions normal, the officer of the deck notes in the log. They are approaching the limit, the classified test depth. This is the moment the engineers have been waiting for. This is where the Thresher proves she is the queen of the deep. But somewhere in the aft section of the ship, in the tangled machinery of the engine room, a microscopic drama is unfolding. The Thresher is a complex organism. She relies on thousands of feet of piping to move seawater through the ship. This water is used for cooling the condensers, for cooling the reactor support systems, and for trim and ballast. At deep depths, this seawater is not a gentle liquid. It is a high-pressure jet, possessed of incredible kinetic energy. The pipes carrying this water range in size from massive mains to small auxiliary lines. They are joined together not by welding, which fuses the metal, but by brazing. Silver brazing is a process similar to soldering, where a silver alloy is melted into the joint between two pipes to seal them. It is an elegant, efficient method, but it relies on perfection. If the pipes are not perfectly clean, or if the heat was not applied evenly during construction, the silver does not bond correctly. It leaves tiny voids, air pockets, inside the joint. As the Thresher goes deeper, the pressure on these joints increases. The hull compresses, shifting the alignment of the pipes. A pipe that was stable at the surface is now being twisted and pulled. At 9:09 a.m., deep in the engine room, one of these silver-brazed joints reaches its breaking point. It is likely a pipe ranging from 2 to 5 inches in diameter, small in the grand scheme of the ship, but large enough to kill it. The silver gives way. The failure is instant. The pipe separates. a jet of seawater blasts into the engine room with the force of a fire hose connected to a cannon. This is not a drip. It is a violent, deafening roar. The water atomizes as it hits the air, filling the compartment with a blinding, freezing mist. The noise is incredible, a screaming hiss that drowns out all communication. The water strikes the electrical panels. Salt water is a perfect conductor of electricity. Short circuits arc and spark. Breakers trip. The lights in the engine room flicker and die. The crew in the engine room reacts with desperate heroism. They try to isolate the leak. But in the dense fog and darkness, with high-pressure water blasting them, it is nearly impossible to find the right valve. More critically, the water spray hits the main electrical switchboards for the reactor coolant pumps. These pumps are the heart of the propulsion system. They keep the reactor cool. When the electrical bus shorts out, the pumps stop. The reactor safety system detects the loss of flow. It does exactly what it was designed to do to prevent a meltdown. It triggers an automatic scram. The control rods slam into the core. The nuclear reaction stops. The steam supply to the turbines is cut off. The propeller slows. The Thresher loses forward motion. Now, the physics of the ocean take over. A submarine maintains its depth by balancing its weight against its buoyancy. But the Thresher is taking on water. Every gallon of seawater that enters the hull adds 8 pounds of weight. She is getting heavier by the second. Without the propeller driving her forward, the planes, the underwater wings that help generate lift, become useless. The Thresher begins to sink. She is heavy, silent, and sliding backward into the dark. In the control room, Captain Harvey feels the boat shudder. He sees the speed indicator drop to 0. He receives the report from the engine room. Flooding, reactor scram. He knows instantly that they are in mortal danger. He has only one option left. He must make the ship lighter. He must blow the main ballast tanks. "Blow main ballast," he orders. The chief of the watch hits the switches. High-pressure air, stored in massive bottles at 4,000 psi, rushes into the ballast tanks. The goal is to displace the water, to replace the heavy seawater with buoyant air. On the surface, the men on the Skylark hear the hiss of the air rushing into the tanks over the underwater telephone. It is the sound of hope. But then, the sound stops. The air system on the Thresher has a fatal flaw. As the high-pressure air expands rapidly through the valves and strainers, it cools down. This is the Joule-Thomson effect. The air gets so cold, so fast, that the moisture in the air freezes instantly. Ice forms in the strainers. Ice forms in the valves. Within seconds, the pipes are clogged with ice. The flow of air is choked off. The blow fails. The Thresher is now heavy, powerless, and unable to make herself light. She is falling. Captain Harvey watches the depth gauge. 1,000 feet, 1,100. The needle is moving steadily into the red zone. He grabs the microphone for the underwater telephone. He tries to communicate with the surface, to tell them what is happening, perhaps to leave a final record for the investigators who will come later. "Experiencing minor difficulty," he says, his voice disciplined, refusing to panic even as the floor tilts beneath him. "Attempting to blow." He knows the blow has failed. He is trying again, cycling the valves, hoping the ice will clear. But the physics are relentless. The Thresher passes her test depth. She passes the safety margin. She enters the crush depth, the theoretical limit where the steel hull can no longer withstand the pressure of the ocean. The hull begins to groan louder now. The metal is crying out. The ribs of the ship are bending. The bulkheads are flexing. The men in the control room stand at their posts. There is nowhere to run. There is no escape pod. There is only the ship and the sea. They look at each other, They think of their wives in Portsmouth, their children in Groton. They think of the sunlight they left 2 hours ago. At 9:17 a.m., the hull of the USS Thresher reaches its ultimate limit. The ocean finds the weakest point. It pushes in. The collapse is instantaneous. It is faster than the speed of sound. The pressure hull implodes, smashing inward with the violence of a bomb. The air inside the ship is compressed in a microsecond, creating a flash of heat as hot as the surface of the sun. The 129 men do not suffer. Their brains do not have time to register the pain. One moment, they are standing in a steel room, fighting to save their ship. The next moment, the ocean has reclaimed the space. The Thresher is gone. The pride of the nuclear navy, the machine that was supposed to be unsinkable, has been reduced to thousands of shards of twisted metal, drifting slowly down to the bottom of the Atlantic, 8,400 feet below. On the surface, the Skylark rocks gently in the swell. The captain lowers his binoculars. The sonar operator takes off his headphones, his face pale. The silence on the radio is absolute. The test is over. The morning is about to begin. When a disaster of this magnitude occurs, the first instinct is to blame the unknown. We want to believe it was a rogue wave, a Soviet torpedo, or a mysterious underwater anomaly. It is comforting to think that the cause was external, something beyond our control. But the truth of the Thresher disaster is far more unsettling. The submarine was destroyed not by a monster in the deep, but by a microscopic flaw in our own engineering philosophy. To understand how the most advanced vessel in the world was lost, we must look away from the dramatic implosion and focus on a small, unassuming connection between two pipes. We must understand the physics of the silver-brazed joint. A nuclear submarine is essentially a complex plumbing project wrapped in steel. There are miles of pipes running through the hull. Some carry hydraulic fluid to move the rudder. Some carry high-pressure air. But the most critical pipes carry seawater. The ocean is the lifeblood of the submarine. It is used to cool the steam condensers, allowing the reactor to generate power. It is used to cool the auxiliary machinery. This means that the submarine must deliberately bring the ocean inside its hull. The pressure inside these seawater pipes is exactly the same as the pressure outside the submarine. At test depth, that pressure is immense, enough to cut through bone. In 1963, the standard method for joining these pipes was silver brazing. It is a process that sits somewhere between soldering and welding. You take two pipes, a male end and a female end, and fit them together. You insert a ring of silver alloy. Then, you heat the joint with a torch until the silver melts and flows into the tiny gap between the pipes by capillary action. When it cools, it forms a solid, watertight seal. On paper, silver brazing is an excellent technique. It is strong, vibration-resistant, and relatively easy to perform. But in practice, it is unforgiving. For the silver to bond correctly, the metal surfaces must be perfectly clean. If there is a speck of grease, a fingerprint, or a patch of oxidation, the silver will not stick. It will flow around the dirt, leaving a void, an air pocket inside the joint. Crucially, you cannot see these voids from the outside. A brazed joint can look perfect to the naked eye, smooth, shiny, and solid, while hiding a fatal weakness deep inside the metal. The Thresher had over 3,000 of these silver brazed joints in her seawater systems. During her construction and overhaul, inspections revealed a disturbing trend. Ultrasonic testing, using sound waves to see inside the metal, showed that a significant percentage of the joints were substandard. Some had voids, some had incomplete bonding. But here is where the tragedy moves from mechanics to culture. The Navy faced a dilemma. To fix every suspicious joint would require ripping the ship apart. It would delay the schedule by months. it would cost millions. The decision was made based on probability. They reasoned that the joints had passed a hydrostatic pressure test in the shipyard. They had held up under pressure once, so they would hold up again. The testing requirement was waived for hundreds of joints. The Thresher was sent to sea with known potential flaws, under the assumption that the safety factor in the design would cover the imperfections. It was a gamble. And on the morning of April 10, 1963, the House won. We can reconstruct the failure with terrifying precision. As the Thresher descended, the hull compressed. The steel ribs of the ship flexed. The piping systems, rigidly attached to the hull, were subjected to twisting and bending forces. Deep in the engine room, one of those substandard silver joints, perhaps a 2-inch line feeding an auxiliary cooling pump, began to stress. The tiny voids inside the silver acted as stress concentrators. Cracks formed. The silver ligament holding the pipes together snapped. The pipe separated. At that depth, the water pressure was roughly 450 pounds per square inch. When the pipe broke, it didn't just leak. A solid column of water, as hard as a steel bar, blasted into the compartment. The chaos that followed was dictated by the layout of the engine room. The Thresher's design was dense. The electrical switchboards were located dangerously close to the seawater piping. It was a design oversight that seems obvious in hindsight, but was standard practice at the time. The spray of salt water hit the electrical bus. The result was an immediate, violent short circuit. The breakers protecting the main coolant pumps tripped to save the equipment. The pumps stopped. This is the critical moment where the reactor safety systems, designed to save the machine, inadvertently doomed the crew. A nuclear reactor must have coolant flow. If the water stops moving, the core overheats and melts down. The system is designed to fail safe. If the pumps stop, the reactor automatically scrams. SCRAM is an acronym from the early days of nuclear physics. Safety, Control Rod, Axeman. It means an immediate emergency shutdown. The magnetic latches holding the control rods release. Gravity and springs slam the rods into the core. The nuclear fire goes out instantly. When the reactor scrams, the steam generation stops. The turbines spin down. The propeller stops turning. The Thresher was now a glider without an engine. Normally, this is a survivable emergency. The crew trains for it. Reactor scram, rig for reduced electrical. You use the battery to power a small emergency propulsion motor. You drive the ship to the surface. But the Thresher was deep. She was heavy with flooding, and the battery propulsion system was weak, designed for creeping, not for driving a heavy, sinking boat upward against the crushing weight of the ocean. There was only one way out: buoyancy. The emergency main ballast blow system is the submarine's parachute. It relies on banks of high-pressure air bottles. When the valves open, this air rushes into the ballast tanks, displacing the water and making the ship light enough to float like a cork. But the Thresher's air system had a fatal design flaw, one that had never been fully appreciated until this moment. The air was stored at 4,500 psi. To enter the ballast tanks, it had to pass through a complex path of pipes, valves, and strainers, filters. As high-pressure air expands rapidly, it cools down. This is basic thermodynamics. The air in the Thresher's banks was not perfectly dry. It contained trace amounts of moisture. When the desperate crew in the control room threw the switches to blow the tanks, the air rushed out. It expanded and cooled instantly, dropping to temperatures far below freezing. The moisture in the air turned to ice. The ice formed on the mesh of the strainers. Within seconds, the strainers were clogged. The roar of the air turned into a wheeze, and then silence. The parachute failed to open. The crew of the Thresher was trapped in a deadly cascade of failures. The bad weld caused the leak. The leak caused the electrical short. The short caused the reactor scram. The scram killed the propulsion, and the ice killed the recovery system. It was a perfect storm of engineering oversights. Each individual system had been designed by brilliant men. The reactor was safe. The hull was strong. The air system was powerful. But no one had stepped back to look at how these systems interacted in a worst-case scenario. No one had asked, what happens if a pipe bursts next to the switchboard? No one had asked, what happens if we blow the tanks for more than 30 seconds? The investigation would later call this a lack of system integration. But in the engine room of the Thresher, as the water level rose and the lights died, it wasn't an academic problem. It was a death sentence. The men in the engine room fought to the end. Forensic analysis suggests they tried to mechanically isolate the leak. They tried to restart the reactor. But the laws of physics imposed a time limit they could not beat. The Thresher was sinking at a steep angle. She was sliding backward. As she passed the crush depth, the hull simply ran out of strength. The implosion that followed was a mercy in a grim sense. It was faster than the nervous system could register. But the terror of the minutes leading up to it, the realization that the machines were failing, one by one, is the true horror of the story. This was not a failure of courage. The crew did everything right. They followed their training. They flipped the switches they were trained to flip. But the switches didn't work. They were betrayed by the blueprints. The silver braze joint, a cheap, simple connection, had held the fate of 129 men. And because it was not verified, because it was assumed to be good enough, it failed. And it took the flagship of the U.S. Navy with it. The ocean keeps its secrets well, but the United States Navy was determined to tear the truth from the seabed. In the weeks following the disappearance of the USS Thresher, the Navy launched one of the most extensive search and salvage operations in maritime history. The bathyscaphe Trieste, a strange-looking deep-diving vessel, descended into the abyss to photograph the wreckage. The images that came back were haunting. A shattered rudder, a twisted section of the sail, a debris field scattered like confetti across the ocean floor. But the physical wreckage was only part of the story. The real investigation was happening in hearing rooms in Washington, D.C. and Portsmouth, New Hampshire. A court of inquiry was convened. Admiral Rickover, the father of the nuclear navy, was called to testify. Shipyard commanders, engineers, and quality control inspectors were put under oath. The question they faced was simple. How could the most advanced ship in history simply vanish? The answer that emerged was not a technical smoking gun. It wasn't a single broken part that doomed the Thresher. It was something far more disturbing. It was a failure of philosophy. The investigation revealed that the culture of submarine construction had not kept pace with the technology of submarine operation. The Navy was building nuclear spaceships with the mindset of a World War II diesel mechanic. The most terrifying truth was that the disaster was not an accident in the traditional sense. It was the inevitable mathematical result of a system built on assumptions. The investigators found that the quality control records for the Thresher were a disaster. During the construction of the submarine, thousands of welds and braze joints were made. Each one was supposed to be inspected and signed off. But when the investigators pulled the files, they found gaps. Signatures were missing. Ultrasonic test results were incomplete. In one chilling exchange, it was revealed that nearly 14 of the silver braze joints that were tested showed defects. Instead of repairing them all, a waiver was issued. The logic was circular. The ship has operated safely so far, therefore the joints must be safe. This is known as the normalization of deviance. It is the slow, creeping acceptance of lower standards because nothing bad has happened yet. The engineers assumed that the safety margins built into the design would cover for the sloppy workmanship. They assumed that a small void in a silver joint wouldn't matter because the steel was so strong. Admiral Rickover was furious. He saw this as a betrayal of the fundamental principles of engineering. In his testimony, he did not mince words. He blamed the disaster on management and workmanship. He argued that the Navy had become enamored with the glamour of new technology, faster missiles, deeper depths, while neglecting the unglamorous, dirty work of quality control. "We have learned that there is no such thing as a small detail," the report concluded. A 2-inch pipe is just as important as the nuclear reactor. If the pipe fails, the ship dies. The investigation also highlighted the failure of the air system. The de-icing problem with the ballast tanks was not unknown. There had been previous reports of strainers freezing up during tests on other submarines, but these reports had been filed away as anomalies. They were seen as nuisances, not fatal flaws. No one had connected the dots. No one had simulated a full emergency blow at maximum depth. The terrifying truth was that the 129 men on the Thresher were test subjects in an experiment they didn't know they were part of. They were sailing a prototype that had not been fully debugged. This realization shook the Navy to its core. It meant that every other submarine in the fleet was a potential coffin. If the Thresher had bad welds, then the Skate had bad welds, and the Seawolf had bad welds. The entire nuclear fleet was suspect. The reaction was swift and brutal. The Navy didn't just write a new manual. It tore down the entire philosophy of submarine safety and rebuilt it from the ground up. They realized that you cannot inspect quality into a product after it is built. You have to build it in. You cannot assume a pipe is safe because it looks safe. You have to prove it. This shift in thinking, from trust to verify, is the most important legacy of the disaster. It marked the end of the era of the gentleman's agreement in shipbuilding, where a foreman's word was good enough. It ushered in the era of documentation. The investigators demanded a new standard, objective quality evidence, OQE. OQE means that you don't just say you did the work, you prove it with data that can be audited. You welded this pipe? Show me the X-ray. Show me the certification of the welder. Show me the batch number of the welding rod. Show me the signature of the inspector who watched you do it. If you cannot produce the paper, the weld does not exist. It must be cut out and done again. This seems bureaucratic. It seems like red tape. But in the unforgiving environment of the deep ocean, red tape is the only thing that keeps the water out. The investigation concluded that the ocean searches for the weak link with a relentless, infinite patience. If there is a single undocumented joint, the pressure will find it. The investigation also changed the way the Navy thought about depth. Before Thresher, the test depth was a target to be hit. After Thresher, it was treated as a boundary that must be respected. The operating depths of existing submarines were restricted. Some boats were never allowed to dive deep again because their hulls could not be retroactively certified. The inquiry was a public confession of failure. It admitted that the United States Navy, the most powerful maritime force in history, had been careless. It had let arrogance replace rigor. But out of this humiliating admission came a resolve that is unique in military history. Usually, after a war or a disaster, organizations tend to cover up their mistakes. They classify the reports. They protect the careers of the admirals. The Navy did the opposite. They took the lessons of the Thresher and codified them into a program that would become the gold standard for high-risk engineering. They decided that the only way to honor the dead was to ensure that the specific chain of failures that killed them could never, ever happen again. The Thresher disaster proved that in the nuclear age, good enough is a death sentence. It proved that complex systems fail in complex ways. And it proved that the only defense against the chaos of the ocean is a fanatical, almost religious devotion to detail. As the findings of the court were released to the grieving families and the shocked public, the message was clear. We broke faith with these men. We sent them out in a machine that was not worthy of them, and we will spend the rest of our existence trying to earn that trust back. From the wreckage of the Thresher and the damning conclusions of the inquiry, the United States Navy forged a new religion. Its name was SubSafe. It is difficult to overstate how radical the SubSafe program was when it was introduced in 1963. In most industries, safety is a set of guidelines. In the post-Thresher submarine force, safety became an absolute binary law. A submarine is either SubSafe certified or it does not submerge. There is no middle ground. There are no waivers for operational necessity. Even in wartime, if a boat cannot prove its integrity, it stays on the surface. The core philosophy of SubSafe is simple: material assurance and recoverability. Material assurance means knowing, with 100% certainty, the pedigree of every component that keeps the water out. It covers the hull, the seawater piping, and the penetrations where cables pass through the steel. Under SubSafe, the era of grab a pipe from the pile ended. Every piece of metal used in a critical system now has to be tracked from the moment it is smelted at the foundry to the moment it is installed on the ship. A mechanic cannot just install a valve. He has to check its serial number against a database to ensure it was tested to the correct pressure. If the number doesn't match, the valve goes in the trash. The program also banned silver brazing on all piping systems greater than a certain diameter. It was replaced with welding, a more difficult, expensive process, but one that creates a monolithic bond that can be easily inspected by X-ray. Recoverability means that even if something fails, the ship must be able to save itself. The Thresher died because she couldn't blow her ballast tanks fast enough. SubSafe mandated a complete redesign of the emergency blow system. The new system was designed to be idiot-proof and physics-proof. The air passages were widened. The strainers were redesigned to prevent icing. The valves were built to snap open instantly. Today, when a modern submarine triggers an emergency blow, it doesn't just hiss, it explodes upward. The ship rockets to the surface with such violence that it can breach out of the water like a whale. It is a ride designed to be terrifying, because the alternative is death. But programs are just paper. The real test of SubSafe came 5 years later, in 1968, with another tragedy that served as a grim validation of the new rules. The USS Scorpion, SSN 589, was a skipjack-class submarine. She was an older boat, built before the Thresher disaster. She was fast and aggressive, but she was tired. In the late 1960s, the Navy was stretched thin by the Cold War and the Vietnam conflict. The operational tempo was brutal. Submarines were needed everywhere. The Scorpion was due for a massive overhaul to bring her up to the new SubSafe standards. It would have been expensive and time-consuming. So, the Navy made a calculated risk. They gave her a restricted availability, a quick tune-up instead of a full rebuild. They did not certify her as SubSafe. Instead, they placed restrictions on her. She was told not to dive to her original test depth. She was told to be careful. On May 22, 1968, the Scorpion disappeared in the Atlantic Ocean, southwest of the Azores. 99 men were lost. The exact cause of the Scorpion's loss is still debated. Some say a torpedo malfunction, others say a battery explosion. But the wreckage tells a familiar story. The boat imploded. She sank past her crush depth and was destroyed. The loss of the Scorpion was the final proof written in blood. It demonstrated that you cannot cheat the ocean. You cannot put warning stickers on the submarine and expect it to be safe. If the hull is not certified, if the pipes are not proven, the boat is vulnerable. The contrast between the two disasters solidified the SubSafe culture. The Thresher proved the need for the program. The Scorpion proved the penalty for ignoring it. Since the loss of the Scorpion in 1968, the United States Navy has not lost a single submarine. Not one. Consider the context of that statistic. For over 50 years, American submarines have operated in the most hostile environments on Earth. They have played cat and mouse with Soviet hunters. They have navigated under the polar ice caps. They have conducted high-speed maneuvers in the deep Atlantic. Millions of dives, hundreds of millions of submerged hours, and every single time they have come back up. This safety record is unparalleled in the history of complex engineering. The Space Shuttle program lost 2 orbiters. Commercial aviation has crashes. But the sub-safe boundary has held. It has held because the program is ruthless. In the shipyards at Groton and Newport News, the sub-safe inspectors are feared more than the admirals. They have the power to stop work on a multi-billion-dollar project because a single signature is missing on a welding form. New workers often complain about the bureaucracy. "I know I welded it right," they say. "Why do I have to fill out 3 forms?" The veterans take them aside and tell them the story of the Thresher. They explain that the forms are not paperwork. They are a contract with the widows of 1963. There is a famous story in the submarine force about the subsafe audit. Every year, independent teams descend on the submarine bases to audit the records. They pick a random valve on a random ship. "Prove to me this is safe," they ask. The crew must produce the documentation. They must show the paper trail that links that specific piece of metal back to the factory. If they can't, the submarine is decertified. It cannot dive. It is chained to the pier until the issue is resolved. This culture of chronic uneasiness is what keeps the fleet alive. Submariners are taught to never be comfortable. They are taught that the ocean is always trying to kill them, and the only shield they have is the integrity of the ship. The subsafe program also changed the way the Navy handles communication. During the Thresher incident, the ambiguity of the phrase "minor difficulty" caused confusion. Today, communications are precise and standardized. There is no room for politeness in an emergency. But perhaps the most profound change is in the concept of responsibility. Before Thresher, safety was seen as the job of the safety officer. After Thresher, safety became the personal responsibility of every single person who touches the boat. The welder knows that his weld is the only thing standing between the crew and the abyss. The supply clerk knows that if he orders the wrong bolt, the hull could fail. The profound weight of the 129 ghosts rests on the shoulders of the entire industrial base. It is a heavy burden, but it is carried with pride. The modern U.S. submarine force is the safest in the world, not because they have better technology, though they do, but because they have better memory. They remember the sound of the implosion. They remember the silence on the Skylark. The Scorpion tragedy, while devastating, underscored that the decision to implement subsafe was correct. It was the line in the sand. The Navy decided that the cost of the program, the billions of dollars, the delays, the endless inspections was worth it. Because the alternative is the sound of a hull crushing at depth. The legacy of the Thresher is not found in a museum or a monument. It is found in the fact that thousands of submariners have deployed, done their duty, and returned home to their families. Every reunion, every retirement ceremony, every grandchild born to a submarine sailor is a direct result of the lessons learned in the dark waters of 1963. The price of safety was 129 lives. It was an agonizingly high price to pay, but the Navy ensured that it was a price that only had to be paid once. 8,400 feet below the surface of the North Atlantic, the darkness is absolute. The water pressure is 3,800 pounds per square inch, enough to compress a styrofoam cup to the size of a thimble. Here, scattered across a wide field of silt and gray mud, lies the physical reality of the USS Thresher. The debris field has been visited many times by robotic explorers and deep submergence vehicles like the Alvin and the Jason. The images they bring back are surreal. The massive sail, the dorsal fin of the submarine, stands upright on the bottom, its number 593 still visible, ghostly white against the black steel. There are sections of the hull, twisted and torn like paper. There are tangles of cable and pipe. But what strikes the observers most is not the violence of the wreckage, but the silence. It is a tomb. The reactor compartment remains intact, a silent sentinel guarding the nuclear fuel that still sits inside, warm with residual radiation, but contained by the heavy shielding. The Navy monitors the site regularly to ensure no radiation leaks into the environment. So far, the engineering has held. Even in death, the Thresher's reactor protects the ocean. This gravesite is a restricted area. No fishing is allowed. No salvage is permitted. It is holy ground for the submarine force. But the true monument to the Thresher is not down there in the cold dark. It is up here, in the light, moving silently through the oceans of the world. The legacy of the Thresher lives in the institutional memory of the United States Navy. Institutional memory is a fragile thing. In most organizations, lessons are learned and then forgotten as the generation that learned them retires. The people who saw the fire die, and the new people only read about it in books. They start to think the rules are old-fashioned. They start to cut corners again. The submarine force fights this forgetting with a ferocity that borders on obsession. Every year, on the anniversary of the loss, ceremonies are held at submarine bases across the country. The names of the 129 men are read aloud. A bell is tolled for each soul. But it goes deeper than ceremonies. The story of the Thresher is woven into the training of every new sailor. When a young officer arrives at nuclear power school, one of the first things he studies is the Thresher accident. He doesn't just learn that it sank. He learns why. He studies the thermodynamics of the icing strainers. He studies the metallurgy of the silver brazing. He is taught that the laws of physics are unforgiving and that the ocean is always waiting for a mistake. This education creates a unique psychological profile. A submariner is trained to be a pessimist. He is trained to look at a valve and ask, "How will this fail?" He is trained to trust his shipmates but verify their work. This is the concept of verifiable trust. It is the idea that I can sleep soundly in my bunk, hundreds of feet underwater, because I know that the person on watch is following the procedure. And I know he is following the procedure because the system does not allow him to deviate. A submariner once explained it simply to a civilian. When I'm 1,000 feet down, I'm trusting people I will never meet. The welder in 1960, the inspector in 1985, the supply clerk in 2005. I am trusting their signatures. Their integrity is the only thing keeping the water out. This chain of trust is the invisible structure that holds the fleet together. It is stronger than the HY-80 steel. The Thresher disaster also changed the relationship between the military and the industrial base. The SubSafe program forced the shipyards to elevate their game. It drove advancements in non-destructive testing, in metallurgy, and in systems engineering. The rigorous standards developed for submarines have bled over into other industries. Nuclear power plants, aerospace, and deep-sea oil exploration. The safety protocols written in the blood of the Thresher crew have likely saved thousands of lives in industries that have nothing to do with war. But ultimately, the story always comes back to the human cost. 129 men. We must remember that they were not just sailors. They were fathers who never came home to throw a baseball. They were husbands whose wives waited on the pier for a ship that never appeared. They were sons whose parents received a telegram instead of a phone call. The grief of the Thresher families was the catalyst for change. Their loss shamed the Navy into action. It forced a proud organization to admit it was wrong and to promise to do better. And they have kept that promise. Since 1963, the United States has built hundreds of nuclear submarines. Sturgeon-class, Los Angeles-class, Ohio-class, Seawolf-class, Virginia-class. These boats have operated in the shallow, littorals and the deepest trenches. They have collided with underwater mountains, tangled with fishing nets, and suffered fires. But none of them have been lost to a material failure. The hull has held. The pipes have held. The blow systems have worked. Every time a submarine surfaces, bursting through the waves in a spray of foam, sunlight glinting off its wet black skin, it is a salute to the Thresher. It is a testament to the fact that we learned. The USS Thresher failed. That is the hard truth. She failed her crew. But that failure was not meaningless. In her death, she birthed a culture of excellence that has protected generations of sailors. The men of the Thresher are still on patrol. They are the silent guardians of the standards. They are the invisible inspectors looking over the shoulder of every welder and every engineer. They are the reason the boats come home. As the sun sets over the Atlantic, casting long shadows over the water where the skylark once waited in vain, we are left with a final thought. Safety is not a manual. It is not a checklist. Safety is a moral obligation. It is the covenant between the builders and the operators, signed in ink and sealed with the memory of the lost. SubSafe is not just a program. It is a monument. And as long as that monument stands, the Thresher will never truly be lost.